Here's 6-2, day 2. Let's see, at the end of day 1, kind of introduce you to the concept of trig identities, kind of a bunch of formulas, more or less, that involve trig functions that we can show or verify that are true. Now, as far as like verifying these, I'm not gonna take you through that for the sake of time. This would get a little bit long if we did, but for a lot of these identities, if you just said, hey, here's an arbitrary right triangle, there's angle theta, we'll call this side x, this side y, this side h. Most of these you could prove fairly easily. Easily meaning like you set up an equation and then use some algebra, and within 2, 3, 4 steps of algebra, you could show that the identity is true. So just know that that aspect is there. I'm not going to do it now, but it's there. Next couple slides, I'm going to take you through simplifying like expressions or equations that have trig functions in them, right? Day 2, you're going to see a ton more of these trig functions: sine, cosine, tangent, secant, cosecant, and cotangent, right? The 6 that you were introduced to in day 1. All right, so for part A here, I'm going to simplify 1 plus cosine A times 1 minus cosine A. I'm going to treat it like a FOIL. Just because if it doesn't match up with like this table and the identities you got the other day, it doesn't really match up with anything, okay? So I'm going to try to FOIL it. Only thing I could think of to do. Let's see, minus cosine A minus cosine squared. Okay, kind of running out of room here for part B, but we'll make that work. All right, middle terms will cancel out, and I'm left with 1 minus cosine squared. I look over to my identities, and basically I'd start with the trig function that I have. Okay, I've simplified this to the point where I've got a cosine squared. I go over to my Pythagorean and say, okay, that looks like the only one that fits. But this is a really big thing, is to remember that when you're going to make a substitution with one of the identities, you can rearrange the terms in the equation. For example, if I were to subtract cosine squared, from both sides, I would get this, okay? Now that matches exactly what I have, so I could finish this one off and say, all right, that whole thing would simplify to sine squared, okay? So particularly with the Pythagorean identities, know that you can do that. It's going to happen one more time in the examples that we're doing here today. Tangent times cosine. I'm going to bump things over just a little bit so we can have a little more room. Okay. Cosine, not much I can do with that. The only thing that really kind of jumps out at me is with tangent, I could use a quotient and say, all right, tangent is sine of A over cosine. That's another one of those identities that I was telling you about at the beginning. If you wanted to prove or verify that tangent is the same as an angle sine value divided by its cosine value, it's not hard to do at all. And multiplying by cosine, those cancel, and that expression would simplify to sine of A. Okay? I'm actually going to jump down and do part B just because, or not part B, part D, just because it's short and it's super simple. It's like, okay, 1 over secant right? That's a reciprocal. I mean, that matches this right here, like, perfectly. That would be cosine. All right, so here's part C, okay? Same kind of thing as part A. It looks like just a FOIL has got to be the only way to go. I don't know exactly where it's going to take me, but I've got nothing else to try. All right, so we get cosecant squared, and then I get plus cotangent B. Whoops, should be cosecant. I got to back up here. I was doing the inner terms. I got to do the outer. I got the first, right? The product of the first two terms is cosecant squared. Then it would be forgot my negative. Cosecant times cotangent, but it's going to be a negative sign in there. So minus plus cotangent B times cosecant B. Oh, I'm going to drop down to the next line here. Minus cotangent squared of B. Okay? Just expands into four terms, but with, the middle two being a product of two different trig functions, it looks long. Okay? However, if you look at those middle two terms, they're each a product of a factor of cosecant and cotangent, but one is positive and one is negative. Which means those will cancel. And we are left with that, okay? Now that I've foiled it out, I'd look to my identities and see, can I use any, right? And the key, usually the answer is yes. When you get to this point, it's like, all right, to simplify it further, I got to substitute an identity. You got to pick the right one, but notice this one has cosecant squared and cotangent squared. So this one's got to be rearranged a little bit, but that's the one that we're going to want, right? It's the only one that has both of those in it. And then if I subtract cotangent squared from both sides, you would get cosecant squared minus cotangent squared, which is the exact case we have here. That whole thing simplifies to 1. All right, we'll try a few more here. By the way, part B, if you notice that one, tangent times cosine equals sine. I don't know what happened there. We can just cross that one out just for the reason that in the previous slide, we did that. So we know tangent times cosine equals sine, okay? All right, part A. First thing that comes to mind here, I'll leave sine of A alone. So I'm starting on the left side and trying to simplify it to get to the right. I'm going to make the move of saying that cosecant is 1 over sine. Those signs would cancel, and sure enough, it's 1. Okay. Same thing here. 1 over secant squared plus 1 over cosine squared equals 1. I'm going to stick with the reciprocal. Okay. Now, even though the reciprocal identities don't show trig functions with powers higher than 1, like 2, what we have in this case, it still works. Okay. So 1 over secant squared we can say that's cosine squared. 1 over cosecant squared, we can call that sine squared. Looks just like our Pythagorean identity, cosine squared plus sine squared. Yes, indeed. That is 1. All right, part D. First thing I'm going to do here is actually go back to the list we had the other day. And I'm going to say right here, cosine of 90 minus A. I'm going to use what's called a cofunction identity. Again, if that one's not listed on this slide, but if you go back to the last slide from yesterday, they're on there. We talked about them, again, right at the end of day 1. All right, so sine A times cosecant minus sine, but the only thing I got is let's distribute this because I got to start working on the left side. So I'll get sine A times cosecant A minus sine squared. Now this part right here reminds me of part A, right? Sine of A times cosecant. It's essentially that's a product of 2 reciprocals, and you'll see that consistently in the problems we'll do in this chapter, that's always 1. If you take a trig function and just multiply by its reciprocal identity. And we are left with 1 minus sine squared, which reminds me of the Pythagorean identity right here again. Okay? And again, it's so important to remember that if you want, you can rearrange terms. If I subtracted sine squared from both sides, on the left side, we'd just be left with cosine. And on the right, we would have 1 minus sine squared. That gets overlooked a lot, right? That with those Pythagorean identities, you can move terms around. It still means the 2 sides are equal. And this is what we were going for. Sure enough, it gets us to cosine squared. All right, we're kind of switching gears from the identities just a little bit to doing some other things with trig functions. And to do that, we're going to need our calculator. Okay, so the first thing I'm going to tell you here is that if you are using your any kind of TA calculator, there's going to be a button somewhere that you're going to find for the mode, because you're going to have 2 possibilities, and this is like the most important thing if you're using your calculator to evaluate trig functions, which is going to happen. Sometimes we like exact trig values. Sometimes we just have to deal with decimal approximations, and our calculator is the way that we do it. The first 2 parts here with A and B, you'd want to be in degree mode, okay? The biggest concern I have about using that calculator to evaluate trig functions is the mode, okay? If mistakes are made, it's usually, a lot of times because you were just in the wrong mode. Now, the reason that needs to be there is when you go to your calculator for part A, now I'm just going to tell you what the answers are here. You should find your calculator, go give these a shot to see if you can get the answers that match mine, okay? See if you can do that. When you type in tangent of 125, right, we know there's 2 ways to measure an angle, and your calculator needs to know that. Are you talking degrees or are you talking radians? And you got to make sure that the calculator is set that when you type in tangent of 125, that your calculator knows that 125 is a degree measurement, not a radian measurement. All right, one other thing you're probably going to find here, this one's kind of intense. Cosecant of 27 degrees, 13 minutes, 47 seconds. Okay, first of all, when you were to type this in, you should be in degree mode still. But to get to cosecant, we just go 1 over, and then we need to put in the reciprocal, which would be sine. Okay, you'll see sine, cosine, and tangent. You'll see those 3 buttons on the calculator. You won't find it cosecant, but that's okay. Okay? Just 1 over sine. Now here, to evaluate, we'd have to have it as a decimal, so we got to go back to our minutes and seconds and say we'd have to do 13 over 60. 47 over 3,600, okay? Give that one a shot by punching it in. You should, if all goes well. It said to round these to 4 decimal places. You should get 2.1855. Okay, so notice on C and D, no more degree measurement, right? You would need to evaluate these. You need to go into the mode button and switch over from degrees to radians, okay? If it's the kind of thing that you need me to show you in class how to do, that's fine, right? If you're just looking for it right now, right? If you have a TI calculator, I'm familiar with most, if not all of them, right? I can find it for you and show you this is how you would switch, because it's something you want to be able to do. This one's really straightforward. 4 pi over 7 should get negative 0.2225. Last but not least, part D. Okay, same kind of thing. It's like, all right, 2/5, right? Which is another good reminder that a radian angle doesn't have to have pi in it. Many times it does. Doesn't have to. Okay? This should be 1 over cosine of 2/5. $1.0857. All right, so now that we have this ability to go and evaluate trig functions on a calculator, we can do some more stuff, okay? For example, find all the missing information. I'm going to start with my angles because that's kind of the most basic. That's got to be 90. Right? You probably remember back from geometry class that the 3 angles in a triangle have to add up to 180 degrees, right? So I got that other one marked as 45. Okay, the next thing I'm after here is I want to find W, okay? And here's how I'm going to do that. I'm going to go from this 45-degree angle and just label these as opposite and adjacent, okay? And then I'm going to say tangent of 45 degrees equals W over 11, okay? Now remember, so you actually won't need the calculator in this one. I was going to say, remember, you could type tangent of 45 degrees, making sure you're in degree mode in your calculator, and you can get what that number is. We multiply both sides by 11. 11 times the tangent of 45 degrees is our missing side length for W. Now, you don't really need the calculator because if you look back in your notes, 45 degrees is kind of a special angle. It's 1, right? So the side length of W would just be 11, okay? Once I have that, I should also get V, but it's a game changer once you have 2 sides. Because now if you wanted to, you can go back and just do the Pythagorean theorem. You don't have to, okay? If you like how you set up that trig equation, you could go and set up a different one and get side length V, which is the hypotenuse. It really doesn't matter. It's up to you. I think doing the trig function once, but then once you can use the Pythagorean theorem is probably the easier way to do it. So I get that V is the square root of 242. Pulling this down here a little bit. I was checking to see if 242 had a perfect square. It does. So there's V, 11 square root 2. Okay. All right, let's do that again over here on this other one. There's my right angle. That one's 30, right? Take care of those right away. Oh, and now let's go for Y. And let's do it from 30 degrees. So we'll say opposite, right? But now I got to use the hypotenuse, right? Because I know it. And you'll see this all the time, that based on the information you're given, the trig function that you'll choose to use will vary. You're not going to use the same one every time. In the previous problem, I wanted the opposite side, but I was given the adjacent side, so I had to use tangent. Over here, I want the opposite side, but I'm given the hypotenuse. Means the trig function I need to use is sine of 30. But very similar deal, 16 times the sine of 30 degrees is going to equal Y. Similar deal. Go to your calculator if you want to. If you look back in your notes, you can see 30 degrees is also kind of a special case. It's a half, okay? It's not like on your calculator you'd go wrong, right? You just would type in sine of 30 degrees and be like, oh, it's a half. I have that in my notes. Either way, it's going to work just fine. Y is 8. And here we are. We're looking for X. And as always seems to be the case in trig, it comes back to that old rascal Pythagoras and his little theorem. Oh, Pythagoras, thanks so much for giving us this wonderful theorem that we just use again and again. Not really, but whatever, we'll use it. Let's see here, 16 squared minus 8 squared, right, would get you to 192. Missing side length would be the square root of 192. Can I reduce that? I can. 92 could be split up as 64 and 3. Now remember, the only reason I care that we can do that is because 64 is what's called a perfect square, right? If you take its square root, it's not some long, ugly decimal. You get a whole number. It's 8. Okay, and that should be, if you get a square root in your answer, you should always be looking for that the number, in our final answer, the number that's left underneath the square root should be as small as possible. Okay, I don't want to leave it as 192. I want to reduce it down to 3. And again, that got split up because 64 times 3 is 92. Let's do another one in an application setting. Okay, so when you see the application situation, please understand the math is the same, right? Just look at the diagram. Can you see the triangle? Right? Here's my angle of 78.3 degrees. Height of the Washington Monument looks to be the opposite side. 115 is the adjacent. So once I see opposite and adjacent, I can tell you tangent is the trig function I'm looking for. It's calling the height of the Washington Monument Y, and the distance from the base is 115. So compare these steps that I'm doing with the previous two problems that we did to see that application or no application doesn't matter. Whether you're finding the missing pieces of a triangle or the height of the Washington Monument, you're talking about the same process from the math point of view. Now this one's a little bit of a different story from the other two, right? Where I said, you know, dealing with 45 degrees and 30 degrees on the previous slide. You can go calculator if you want to. You've got them in your notes, okay? An exact trig value for tangent of 78.3. You don't have it in your notes, okay? It's not there. This one you got to go calculator, okay? You got to go calculator, but should get about 555.3, but that's where that answer's coming from. Whoops, need a new page. Not only a new page, the last page, last slide. Okay? So, interesting deal here. This will be something we need to get into more. Okay? Because this one has something going on that you don't really have to know the ins and outs of it yet, but it's different from the others, right? Here's the lighthouse, 200 feet from the path. The walkway is, yards, 200 yards. Walkway is 400 yards. You are looking for this, right? Big difference on this. You're looking for an angle, not a side length. The last 3 problems we've worked through, okay, we were looking mostly for side lengths. When we found angles, it was because we already had one, right? I'd love to just subtract this angle right here from 90, but I don't have it, right? I can't do that process that I did on 2 slides ago. Here's what I do know, though, from angle theta. I know the opposite side. I know the hypotenuse, so it tells me this. I don't know theta. I do know that its sine value is 200 over 400. Okay? Now we could certainly reduce that and get it down to a half. Okay? What we need technically, and we'll have to get into this as time goes on, is we need what's called the inverse. Now we've seen the inverse before. We saw it a lot with functions. Inverse comes up when you want to go backwards, essentially, and that's exactly what's happening. A trig function, we would give an angle, and it gives us a trig value. We have the trig value. We want the angle. Okay? So what would happen here is I would take sine inverse of both sides, right? So this would be kind of the algebra side. So I'd take an inverse, and then over here I would take sine inverse of a half. Inverse sine and sine cancel. So this question, I mean, I like it written out like this because it's asking the right question. What angle has a sine value of a half? Okay, there is a way to do this on the calculator. We'll get there, okay? We don't need it on this one because, again, it goes back to kind of a special case of an angle that we know. If you were to look back in your notes, you would see, oh, what angle has a sine value of 1/2? 30 degrees, right? I just went in reverse order, right? On 2 slides ago, I used the fact that the sine of 30 is a half to get a side length. Here I just had to use that sine value to get the angle, okay? That process of doing that, okay? Well, there's a way to do it on the calculator. We'll get into this more, but this whole problem and the process of doing that is called using an inverse trig function. Instead of angle to trig value, take me back to the missing angle. All right, that's it for day 2. More to come in 6-3.